Why do oil and water separate the way they do? Here's a picture. Here's the oil and here's the water. You can put this in a container with a lid, you can shake it up, mix them together. You set it down, what happens? They separate out again. There's something about the water that causes it to bunch up and exclude the oil. And we're going to look at what that is. So here is a Lewis structure for water, and we've talked about how to do that, and about how to predict the shapes of these molecules as well. And that's all going to play into this. So here between the hydrogen and the oxygen, we have a pair of electrons being shared. But sharing is not always equal, is it? Like sometimes when my husband and I share the bed, right? It's like he's got a much larger piece of it, and I'm way over on the edge, even though it's a big bed. But we're sharing it, but it's not equal. And so when two atoms share a pair of electrons, it's also not equal. In this case, the oxygen is taking more than its share of that electron pair. The electrons are spending more time close to the oxygen than they are to the hydrogen. And this has to do with electronegativity. Electronegativity is a word we use to describe the ability, I'm trying to underline, but it's not letting me. Come on. Electronegativity. The ability of an element to attract electrons within a covalent bond. And electronegativity it's a relative scale. The most electronegative element is just assigned a number of 4, and then everything else is compared to that. So fluorine is the most electronegative element, and it's just assigned 4.0, and then everything else is less than that. So when we have unequal sharing, here's that hydrogen and that's the oxygen. Oxygen and hydrogen. And this is one of those electron density type drawings where the darker shows where the electrons are more. And we see that this shape here is not symmetrical. The electrons are spending more time around the oxygen than they are around the hydrogen. So in chemistry land, this is like the two little boys that live near each other. And there's boy 1 and there's boy 2. And boy 1 lives at the O house and boy 2 lives at the H house. And these guys are going to play together. Well, at the O house, they have an in-ground swimming pool with a slide and a diving board, and there's a trampoline in the backyard too. And inside they've got the big plasma screen TV. They've got all the video game consoles. If you're hungry, Mom will have pizza delivered. And they actually have a soda fountain in the kitchen. And they've got like 6 different kinds of soda, and they've all got caffeine in it, right? So it's just an awesome place for little boys to play. At H's house, they have a sprinkler in the backyard and a swing set. And they don't have any video games. And they just have a little television with an antenna. And if you're hungry, Mom will make you a peanut butter sandwich and give you a glass of milk. Where are those two little boys going to spend more time? They're going to go to O's house most of the time. Are they ever going to go over here? Well, yeah, occasionally. This guy wants to say hi to his mom and needs to change his underwear periodically. But most of the time, they're going to be over at the O house. They are not being shared equally, right? And so that's the situation here with the electrons. The oxygen is more attractive to the electrons, just like the O house is more attractive to those little boys. The oxygen is more electronegative. Well, those electrons have charges, right? They have negative charges. And when they spend more time over here, we get a partial negative charge over here. If this little guy disowned his family and got adopted by oxygen, we would have an ionic situation where we would have oxygen with a negative charge and hydrogen with a positive charge. That's not what we're talking about here. It's a partial charge. So this Greek letter delta is used to indicate a partial charge. So this is a partial negative charge. It's between 0 and 1. And this is a partial positive charge. And exactly what that charge is doesn't matter. It's just between 0 and 1. And so we say that this bond has a dipole moment, a separation of charge. There's a negative end and a positive end. Any questions? Personally, I want directions to O's house because I'd like to go hang out there too. So when we have a covalent bond that has a dipole moment, we call it a polar covalent bond. What do you think of when you hear the word polar? Cold. You think of polar generally referring to like the North Pole. Somebody yesterday said bears. Like, okay, polar bears, right? Where do polar bears live? At the North Pole. It's cold at the North Pole. Why do we talk about the North Pole and the South Pole? What's different about those on our planet? They're at opposite ends, and that's kind of an odd concept, right? Because our planet is a sphere, right? So why are those ends chosen? Has to do with magnetism. There's magnetic fields on our planet. That's why a compass always points north, because it lines up with the magnetic fields. So magnetically, North Pole and South Pole are different. In a polar covalent bond, one end of the bond is different from the other end. So that's the idea of polar. Now we talked about electronegativity. If the difference between those two little boys' houses is small, then the difference in time they spend between each house is also going to be small. They're going to spend more time equally. If the difference is large, then it becomes more lopsided. So with the atoms, if the two different elements in that bond have a large electronegativity difference, the bond will be very polar. And if the difference is small, it will be less polar. So here is a graph, or a table, I guess it's a graph, showing electronegativity values for the main group elements in the periodic table. The noble gases are over here because they don't form bonds much at all, and so essentially they have no electronegativity. Here's fluorine. Fluorine's at the top of the hill, 4.0, and it goes down from there. And there's a pattern, just like we saw with periodic trends. As we go down in a group, the electronegativity decreases. As we go across a period, the electronegativity increases. Of course, hydrogen has to be an exception to everything. There are a few where you have two elements that have the same electronegativity, like carbon is 2.5 and sulfur is 2.5. So if you had a bond between carbon and sulfur, it's going to be nonpolar because they're equally attractive. But most of the time, you can assume that between two different elements, it's going to be polar. If we have the same electronegativity, the same attraction for the electrons will be shared equally. There's no dipole moment. And so we call that a non-polar bond, non-polar covalent bond. Anytime you have two identical elements, we've got chlorine and chlorine, obviously, hopefully it's obvious, the difference in polarity will be zero, and so they're going to be a non-polar bond. You may need to refer to that chart showing the actual electronegativity values for some of the homework problems. We won't be using that for an exam. If there's a really large difference, then the electron is actually taken from the one atom and given to the other permanently, and then you have an ionic bond. So that's one extreme. The other extreme was the purely covalent bond where things are shared equally. The ionic bond is when you have a metal and a nonmetal, and we've learned that previously. In between, even sharing and actual transfer is where we have the polar covalent bond. And these are very common between nonmetals. So what we're going to do is we're going to assume that if these two elements are different and they are both nonmetals, we're going to assume that it is a polar covalent bond. And that assumption works most of the time. So it's actually a continuum between electronegativity difference of 0, which would be when you have two identical atoms, like two hydrogens or two chlorines. To the other extreme, the largest difference we can get is a 3.3. And so we've kind of arbitrarily drawn divisions here, and we say 0 to 0.4 is a nonpolar bond, 0.4 to 2 being the difference is polar, and 2 to 3.3 is considered an ionic bond. But this is what I want you to know. Let me see if I can get a color that I can see. The ionic bonds involve a metal and nonmetal. And the nonpolar is the same element. So two hydrogens, two nitrogens, the same. And in here, two nonmetals that are different. Polar covalent. So if you look at a bond, if the two elements are the same element, that's a nonpolar covalent bond. If the two elements are different, but they're both nonmetals, it's polar covalent. If one element is a metal, it's an ionic bond. Any questions? So we should be able to answer questions like this using just a periodic table. So determine whether the bond formed between each pairs of atoms is pure covalent, meaning nonpolar, covalent, polar covalent, or ionic. Between iodine and iodine, that's going to be nonpolar because they're the same. Obviously, they have to have the same electronegativity. We don't want red. So that's nonpolar or pure covalent. How about between cesium and bromine? Ionic, because cesium is a metal. A metal and a nonmetal make ionic bonds. How about phosphorus and oxygen? Polar covalent. Okay? Now you can have polar bonds, but then we also have to think about, well, what about the whole molecule? Is the molecule polar? Does it have a positive end and a negative end? You can have a molecule that has polar bonds, and yet the whole thing is nonpolar. So when we talk about a polar molecule, we say it has a net dipole moment, meaning that the polar bonds are going to add together instead of canceling each other out. For diatomic molecules, it's relatively simple. Diatomic meaning two atoms. If the bond is polar, the molecule's polar. A little more complicated when you get to 3 or more atoms. We have to consider the shape, the geometry of the molecule as well. Let's look at carbon dioxide. This carbon-oxygen bond, is that a polar bond? We've got two nonmetals. That's a polar bond. Okay, so polar covalent bond here, polar covalent bond here. Which atom is more electronegative, the oxygen or the carbon? The oxygen. Oxygen's closer to fluorine on the periodic table. And so this bond is polar in this direction. Here, the arrow, it's like somebody out, you're looking for these two little boys. And somebody comes out and you're walking on the street. Hey, where did Johnny and Tommy go? And you point at the cool house, right? They went to the old house. I'm sure that's where they are. They're always over there. This arrow is like someone pointing at the more electronegative element. That's where the electrons are drawn. The other end of this has a little plus on it. This is the positive end of the bond and the negative end. So here the direction of pull is to the left, and here it's to the right. So imagine that you've got some people playing tug-of-war. You got a guy standing here in the middle, and you've got a guy pulling this way, and a guy pulling that way. Are they going to go anywhere? If they're equal strength? Nope. That guy in the middle is just going to be pulled, right? But he's not actually going to move. If this one was stronger than this guy, then the whole thing might move to this direction. But this guy's being pulled in opposite directions. These vectors cancel each other out. Let's think of a number line. And so here we have this arrow going that way, and we have an arrow going this way, and they're each too long. What does that add up to? -2 and +2 adds up to 0, right? We say that these vectors cancel each other out. I didn't draw them very well, but I think you get the idea. Because carbon dioxide has a linear geometry, the polar bonds cancel each other out. The molecule as a whole is nonpolar. It doesn't have a positive end and a negative end. So here's the explanation of some of those things, the arrows. And that amounts to vector addition, if you remember that from math class, vector addition. Those arrows point in the direction of the negative pole of the polar bond with the plus sign at the positive. If we have arrows going in exactly opposite directions, then they're going to cancel each other out. A vector is a direction and a magnitude. Let's look at water. We looked at water and we now understand that water has a bent shape, right? Here's the model of it, and here's the structure or the formula showing the shape. The hydrogen-oxygen bond is polar, and it points in the direction of the oxygen. And this one points in that direction. One way we can think about this is by separating this vector into 2 points, because this is into 2 vectors, I'm sorry. This is going at an angle. And so you imagine that you're in town where the streets are laid out on a grid, and you're trying to get from point A to point B. But you can't go diagonally through people's yards with your car. You have to go on the streets, right? So you're starting here, and you go this way, right? And then you go up. And we can imagine the same thing happening on the other side with this other vector, where you're starting here, and you go like 3 blocks that way, and 3 blocks up. Oh, that was supposed to be the same color. It's not. Now we can look at these vectors separately. We can look at the red ones and the green ones separately. This is a little hard to compare the blue ones because they're at an angle. These green ones, this one's going to the right, this one's going to the left. Do those cancel each other out? They do. They're going in opposite directions and they're the same length. What about the red ones? The red ones don't cancel out. In fact, they add together. So it would be double when you put those together. So these dipoles do not cancel out, and water is a polar molecule. The oxygen end is slightly negative because it has more attraction for the electrons in the bonds, and the hydrogen side is slightly positive. Because it's more electronegative. It's more attractive to the electrons.
Okay.
So here's looking at these shapes related from Vesper theory relative to polarity. So if we have a linear molecule and these atoms that are bonded to the central atom are the same, it's going to be nonpolar because it's going to cancel out. If we have a trigonal planar molecule and all of these are the same, they're going to cancel out. If we have a tetrahedral molecule and all of these are the same, it's going to cancel out. It's a little more complicated because it's three-dimensional, but it's the same idea. It's symmetrical, and we have this tugging in opposite symmetrical directions, and so the vectors, the arrows cancel out. If we have a trigonal pyramid structure or a bent structure, no matter what happens, these are going to be polar because it's lopsided. So determining whether a molecule is polar, first decide if it has polar bonds. If it has nonpolar bonds, then the molecule is going to be nonpolar. So if the bonding atoms have different electronegativities, polar bonds, then decide whether the polar bonds add up to form a net dipole moment, or do they cancel each other out? And that's where you have to use Vesper theory to figure out what the geometry is, and then look at whether the molecule is symmetrical. Or you can use Mrs. K's alternate method for determining molecular polarity. You need the Lewis structure. Look at the Lewis structure. The molecule is nonpolar if both of these things are true. No lone pairs on the central atom. The atoms bonded to the central atom are the same, or they have the same electronegativities. So let's do it this way. Determine whether CH4 is polar. Well, we need the Lewis structure. So it's going to end up like this. There's the Lewis structure. We look at the Lewis structure and we ask ourselves, are there any lone pairs on the central atom? You see any lone pairs? Any dots? Nope, no lone pairs. Are the atoms bonded to the central atom the same? They are. Both the conditions are met. This is a nonpolar molecule. My alternate method works most of the time. This has a tetrahedral shape, and it's symmetrical. And so even though these are polar bonds, they would be pointing here towards the carbon. Even though they're polar bonds, all those arrows pointing from equally spaced directions to the same point are going to cancel each other out. So that's nonpolar. So we come up with the same answer. Let's look at NH3. This is the Lewis structure. Are there lone pairs on the central atom? Yes. Okay, so that first criteria is not true, so then this is a polar molecule. So the set of rules are great, but it doesn't really help us to understand why. But perhaps you're not that interested in understanding why. That's fine. There are 4 groups around the central atom, 3 bonds and a lone pair. So those things will arrange themselves in a tetrahedral shape. Is this symmetrical, though? No, because there's a lone pair up here. That makes it not symmetrical. So we do have these polar bonds, but this isn't a bond. And so it's going to be lopsided. It's going to be polar. Let's look at SO2. Let's remember to enter drawing mode. Sulfur in the middle, oxygen, oxygen. We did this one. That's the Lewis structure. polar or nonpolar? Polar, because it's got a lone pair on the central atom. So we look at this, and we've got these bonds. There's a lone pair here. When there's a lone pair on the central atom, it's going to be lopsided. It just is. And that's why that rule works. What geometry are these three groups going to form? Trigonal pyramid, right? Sorry, trigonal planar. So a double bond and a single bond, and here's our lone pair. Is that lopsided? Yeah, it is. These are not the same. They're spaced out nice and equally, but they're not the same. The lone pair is different. So this is a polar molecule. Let's do one more. What about that guy? Are there lone pairs on the central atom? No. I guess I should probably put the lone pairs on this guy. He's got lone pairs. We don't care about those. We're looking at the central atom. No lone pairs. Are the atoms bonded to the central atom the same? Yes. What about this guy? We've got 3 hydrogens and chlorine. Do hydrogen and chlorine have the same electronegativity? No, they don't. So this one is also going to be polar. And if we draw this and think about its geometry, it's got 4 groups, right? So it's going to make a tetrahedral shape. So those are the hydrogens. And this guy's different. So the electrons in the bonds are arranged symmetrically, but this guy's different, and so the molecule is not symmetrical, and so it's a polar molecule. And actually, this one, the orientation of the dipole is different, because the chlorine is more electronegative than the carbon is. And so those definitely do not add up to 0. So things that are nonpolar molecules are going to be very symmetrical. They're not going to be lopsided at all. Any questions? So what does this have to do with the oil and water not mixing? Well, like we just determined, water molecules are polar. Look at it, and it's bent, and these are polar bonds. This end is a little bit negative, and the hydrogen end is a little bit positive. Oil molecules are nonpolar. Nonpolar and polar don't mix up very well. Polar molecules interact quite strongly with each other because there's this attraction between these charges. Yes, it's a partial charge, but it is a charge. And so there's an attraction, just like these are supposed to be magnets. Just like 2 magnets are attracted to each other, the south end and the north end, they go click and stick together. Polar molecules act a lot like magnets, and they just want to stick together. I think this is a great illustration. I wish I'd thought of it. It's in the book. So here we have the solid colored marbles are magnetic marbles, and the multicolored marbles are glass marbles. The magnetic marbles clump together. They're attracted to each other. The glass marbles, not so much. So imagine what would happen if you threw a whole bunch of glass and magnetic marbles together in a box. All of the magnetic ones are going to clump up together, right? Are you going to find glass ones in between here? No, they're going to get pushed out, right? It's a, you know, if we want to do crazy analogies, we could say this is a group of really tight friends. They have really strong relationships with each other. They really like each other a lot. And these are the people, they would love to be included in this group. But these guys are so into themselves, they don't even know these people exist. You just can't, it's like a clique. You just can't get into it. You're on the outside. You just don't interact with them in the way that they interact with each other, and so they exclude you. So these polar molecules is like an exclusive club. They're just very attracted to each other. And so when you've got oil and water, the water molecules stick together like these magnetic marbles, and they push the oil out. The oil is floating because the oil is less dense. There are other nonpolar substances that are more dense than water. They also get pushed out, but they'll get pushed out to the bottom, and the water will float on top of that. Now, you probably know that if you have grease or oil or butter or Crisco or something on your hands, you can't get it off just with water, right? Water doesn't do anything to grease. What do you need? You need soap. Because the grease is nonpolar, and it doesn't wash away in the soap. In the water. It does wash away with soap. Sugar, on the other hand, if you've got, been eating Sour Patch Kids or a powdered sugar donut and you've got sugar on your fingers, sugar washes off really nicely with water, doesn't it? Because sugar is soluble in water. Grease isn't. But soap is cool stuff. Soap has a polar head, so this interacts with water really well because it has positive and negative charges on it, positive and partial negative, and so it can be attracted to the water. And then it's got this long tail that is nonpolar and is very much like the grease and oil molecules. And so this can interact with the grease and oil molecules. And what happens is it forms a micelle. And so you'll get these polar heads, and then you've got the little tails. And they're going to, it's like circling the wagons that the pioneers did. And of course, it's going to do this in 3 dimensions, not in 2 dimensions. The grease molecules are going to be very comfortable in here with this other nonpolar tail, which interacts well with the grease molecules. Now it's surrounded by these polar heads. The polar heads can mix with the water. And so it takes the grease that's stuck on your hand and makes it into small pieces, so small that you really can't see them, into small pieces that can get washed away. So it's like a transport carrier almost. The soap comes around the little the grease and allows it to move around in the water. And I think that's the end of chapter 10.